Oh. So okay, so we have this sort of GLN action on cohomology Quasimaps from half of T star flag. And so this is my favorite. This is my favorite question. One of my favorite questions in mathematics. You know, however you're gonna think about this. However you're gonna think about this kind of Coulomb branch business, then maybe you can upgrade it to some kind of critical theory. All of T star flag by some sort of dimensional reduction. But what we would like to get from this, I mean, what I would like to get, what I like, is to somehow we want to get from this is the actual fully equivalent count. And similarly, for any DTKH2. So there's this, we have this biaxial fully equate, but I mean this, what Mina calls the vertex. And I call, following Mina, I also call the vertex. So in other words, this object is some kind of, this object is some sort of, some kind of QQ character. So it has one more, since you can start with T star flag, there was one more, you scale, there's one more equivariance, you can scale by h bar. Well, we usually scale by h bar inverse. So there's one more equivariance, which is the most important equivariance here, which is not uncounted here. And so this is, of course, this is I talk about this topic often, and I don't have so much more to say, but I wanted to review something that many years ago, somehow in Nigut's first paper, addresses this topic in the following fashion, that this is says in this setting, this is your flag, this is saying I want to compute, it says compute, this is the same. So since, what am I supposed to say? So this is if I have the space of Quasimaps, then we so this is the this vertex function here is just the integral over the space of Quasimaps. Maybe there's some kind of z degree. And then the difference between, so since all my, so by localization, all the non-trivial Quasimaps to T star flag, they literally land, I can put them all to the flag. And so then it's just the extra abstraction bundle. And this is to say, and here I will take the Chern polynomial of the tangent bundle, and then I give myself a new variable. Maybe call it, I don't know. So call it whatever you want to like. Maybe call it more or less h bar, or maybe call it, I don't know, u. U is in the Lie algebra of C star h bar, something like that. So I'm looking for, so out of my representation, I want to make a new representation. Sorry, out of my representation, I want to take some kind of new notion of character. And that new notion of character is, what is it supposed to measure? It's supposed to depend on one more variable. And the way, so this is, I'm explaining what's a QQ character. So it's supposed to be one more variable. And what is that supposed to be? So this is, so if I have my space somehow geometrically realized, then I can look at, first of all, I can look at, usually character. Character means I record the multiplicity of weights for maybe a torus, or if I have some kind of loop torus, I can take that. And so my loop torus comes from the Chern classes of all the vector bundles and the covariant homology, covariant K theory. The joint, the generalized eigenspaces of multiplication by all Chern class of all tautological bundles. They're the fixed loci of whatever group elements I have. I look at their fixed points, and their homology or K theory. Those are the generalized eigenspaces for the operators of multiplication homology, or connected components of those spaces. But now, ordinarily, if I want to take a character or a super character, if I have some kind of homology, then if I have a space, I take its Euler characteristic. So if my action is on cohomology or K theory, and in the end, when I'm done with all equations, I just have a space. I take its Euler characteristic, because the alternating rank of cohomology, this is multiplicity of. But I can give myself one more variable by saying I'm going to take the equivariant chi-y genus, and the y in that genus is roughly this variable here. So that will be in K theory. In cohomology, I take this sort of thing. Because you have some space, you can take the equivariant chi-y genus. This sort of thing. And y is the name of the variable. And here it will be u. You want to call it y? Okay. And so now, so this is if. So this is how we're going to proceed now. So now we say that we want to say that this is a trace of some operator. How we're going to proceed. So this is an integral over the diagonal in Quasimaps and Quasimaps, and this is the diagonal. So in general, if I have some so like if you have like with integral operators, you have an integral operator, its trace is the integral of the kernel of the diagonal. Like for instance, if space is finite, then every operator is integral and its trace is sum of the diagonal matrix elements. And so this is, what is this operator? This operator is just polarize this. So this is, say, I take like this is like the trace, z to the degree. And then I take the operator, which I take the Euler class of this. So if this is my V. Prime, and then I tensor. Because this is some operator on the product. And so if I take restricted diagonal, then this expression becomes the tangent bundle. And then I twist it, this becomes this. Right? So in particular, for y equals 0, this is this G. Euler class, I mean, this is the same thing. This is the Chern polynomial. It's the Euler class of a bundle twisted by a current wave. So this is an homogeneous expression, but it's homogeneous if you take the Chern classes here and the powers of y. And the way to think about it, you take is the top Chern class of a bundle which has an current wave. So in particular, there is if you take the constant term in y, this would be the top Chern class of that. So this is for y equals 0. That's just the trace of G. But then I claim for y equals some multiple of epsilon. There's also a formula. And so this is, and the way it works is the following. And this is somehow, there's nothing, the only specific, oh man, I'll injure myself a little bit here. It's okay. So the only specific about flag manifolds here is that this is I somehow, my space, I'm using the fact that there's some kind of global Euler class that defines it. But in principle, there's some, if you, instead of taking that Euler class, you can take the virtual, so instead of the Euler class, you can take the virtual fundamental class or virtual structure sheaf of the inclusion one another. That would be the same. It will have the same effect. And so now we took a half. We took 1/2 of quiver for T star flag such that the framing spaces only receive maps. So when we choose a half of some quiver, it's our freedom to whether the framing spaces send out maps or receive maps. We choose this half. And that this has the effect that if I look at the formula for how was the FK was acting, so how was FK acting? So we went through this exercise, and I just want Without glasses, I have to find the relevant formula in my notes. So I had the notation was I had this is the one with the larger degree that goes into the smaller degree, and then there's delta E. So this was if k acts by the Euler class of what? Of this V prime, which is where so Fk goes from here to there. This is so starts with the bigger degree and lower degree. What? Because this is, I mean, degree of a map is minus the degree of the bundle. But this guy here has no framing here. No framing. And so it means the framing enters this only through self-x, which just really doesn't matter because we're not really moving. Framing really doesn't change. This framing really doesn't enter here, or rather enters maybe only through here. Enters, only self-x. In some sense, that doesn't matter at all, because we're not moving that space. So it's self-x. This doesn't really matter. And so that says that if I have any kind of map that keeps all the v's themselves and changes the framing, then this map commutes with the action of fk's. And how can I have a map like that? Well, I can have my map. And so this is again, this is just general thing. I have my map. Well, I can either just twist, so I can either take this guy and include it in twist by 0, or I can have, or equivalently, I can take all these guys and move them down. Either way around, either way. Well, let's just stick with that. I can twist it down. So this says take my maps as before. The only thing we do, we just increase the framing. Okay? So this map, what does it do? It commutes with FIs, changes by our computation, changes the changes the degree by, well, depends on how you're going to count that. So the actual SLN degree is somehow the degree by a fixed amount. The way written, it doesn't change the degree, but of course, now then you have to somehow recalculate. Better twist it down, then it does change the degree. And so this means what? You have an operator that that uh, that uh, uh, changes, not the degree, maybe changes the eigenvalues of hi by a fixed amount. That means what? This means that this particular operator is the lowest weight vector in some space of operators. So you have an operator that takes a Quasimap and just twists up the framing, or equivalently twist down all the steps and that this operator will commute with the raising operators and has a specific commutation relation with the diagonal matrix elements, with the Cartan elements. That means that if I look at the representation space generated by this operator, this will be a highest weight representation with this, or lowest weight representation with this lowest weight. It's as long, and if you change it by a line boundary, it doesn't matter anything. It doesn't really matter. Or like I said, you can let's do. No, it doesn't have to be. It doesn't have to be. The representation doesn't really matter. I mean, it's just the W will have its own weights, and yeah, that's for that Verma. Yeah, because the modification only happened at the origin. So it doesn't really matter what's the global nature of that bundle. The origin is trivial. All right. Now I have to. And so that means what? That I have my Verma as some kind of operator. Let's call it iota. It's an operator of the following kind. I have a Verma. There's an intertwining operator with Verma. What's the highest weights here will be just the some fixed, maybe the nth symmetric power of the defining representation, something like that. I forgot. So maybe some symmetric power. Maybe the nth symmetric power. And then here we just take the coefficient. This is the lowest weight vector, so take the lowest coefficient. So this is just take the Verma by lowest or highest somehow. And so then when you take, in other words, this is some sort of what people back in the days when Ettingov and Kirillov wrote about this and Nikita wrote about this and some. This was studied also like a century ago, but not to say, many years ago when we were. And so this people call something like vertex operator. It kind of makes sense because this will, by this argument, not only it commutes with FKs, it will also commute with, well, suitably commute with all of its twists, with all of the kind of loop brothers of FK. So it kind of makes sense that this is this is the lowest weight vector in some kind of loop sense. Here. So this is a reduced representation. It has a highest weight vector and lowest weight vector. It's like, So what we use that lowest weight vector? So it just says, so you have so what does it mean? You have an operator in your space. You have some operator that when you commute with your group generates some fine dimensional space of operators. That means how you write that fine dimensional space of operators. you can say that I have a map from my verb tens are a five-dimensional representation. Or you can move with the representation that side, but it doesn't really matter. You can write it this side. So you have to have a finite dimensional space of operators is the same to have a map like that. And now my operator is one particular element in that space, namely correspond to the lowest weight vector here. Yes, a finite-dimensional representation. So if you suppose you have an operator, so your group acts on the space, and group acts on operators on that space, right? And so suppose you have an operator that commutes with all lower-rank operators and has a particular commutational relation with the Cartan elements. This says what? This says that the vector of a certain weight, which is therefore, in addition, lowest weight. Right? That means it will generate if you apply. Yeah, exactly. Yeah. And so then this is two. So what you get that for y equals ka, you're gonna get the trace. So you're gonna get the trace of z to the degree. And if I write it correctly, so let me see. What? I think so. I think so. Not the symmetric part. So I'll take the power of that element. So I think you get my understanding, because it's going to be a trace of the degree, then this iota, or whatever, maybe call it vertex operator. Let's call it v for the vertex. This v to the power k, and then g. And so this is the kind of stuff. This is sort of the kind of stuff. So usually people study traces of traces. So this is one has one big advantage over the usual study of traces of intertwining operators, because the traces of intertwining operators have been studied by Varchenko and Okounkov in some kind of great generality under the rubric of dynamical Weyl groups. But there they study. So if we take the trace, then it only, this operator better be of zero weight, right? Because otherwise the trace. So if if you're tracing some space, only diagonal matrix elements matter. But the but diagonal matrix element, we have to preserve the weight, and so that's. But the zero weight. I mean, if you multiply, if you look at representations, the zero weights, they're somewhere in the middle. They have big multiplicity, and so if you're saying I have some operator which is of zero weight in some representation, well, generally speaking, some representation, this particular representation has one-dimensional zero weight, but in general, if I have some space of operators, then the zero weight in that space is the space of maximal dimension. And so, well, here is written what? Here we still take a trace, but we're written there's some specific God that was like all upper triangular, and so that's going to mix all the weights together. This is certainly not preserve a weight at all. But this one also is not preserve a weight, but this is easier because here we can just, since there's we're going to the highest weight, we can just raise it to some power k. We don't really care. And well, of course, this is you write it like this. It's just the same thing as before. It's some kind of intertwining operator. This is an element in my group. This is an element in my group. They just multiply together to an element in my group, which I can diagonalize. And then I diagonalize this guy. Okay, this would be whatever zero weight. And the trace only the zero weight will survive. But in principle, this sort of language where you have the difference between like Nigut setup and this Varchenko-Okounkov setup is the presence of this element G. And like I said, I think it really helps you because it makes certain things much easier. And now, what I'm trying to say here, I'm trying to say here is that is that is that when we studied this vertex function, we wrote down two different equations for them, and these two different equations have the shape of the dynamical Weyl group. We had to generalize the notion of dynamical Weyl group, but anyhow, that have that shape. However, we arrived at this by just completely other direction somehow. No connection to how Okounkov and Varchenko were thinking about this difference equation. Whereas something like this, as far as I can tell, yeah, should work in much greater generality. So you should be able to write this vertex function in the form as a trace of some vertex operator. So I think it's yeah, I think it's somehow. I would think it's not a bad project for 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 to revisit and to reevaluate. Anyhow, so now that you're probably all very refreshed from the previous discussion, now let me let me talk about something else, unrelated, slightly related. Maybe slow down. Yeah. Yeah. I think I understood the first part, but then this I need a little more time. So first the insertion of this vertex of I think the story you're telling now. It's gotta be this must be related to the stuff with Shamil. In other words, there's the fact that you got McDonald's theory as some, in particular, that kind of vertex operator. I mean, it certainly will. Yeah, this will be some McDonald, this will be some Jack Predol McDonald. Yeah, exactly. Yeah. That's right. But I'm just saying that there's a story like this, I think, for any quiver. No, with G it's still McDonald Primo. Still McDonald Primo. No, not in this formulation. No. So there's some, to my mind. This is just like ordinary McDonald Primo. This is not. This is not the Hyman's. This is like a McDonald. No, not really. No. No, all I'm saying is in that story, the way I try to present it now, is try to present it in a way which is how uses no specific features other than so the fact that you made this step was so this step is I think for general quiver is still okay as long as you're not insist on this on another class, but just say well, this is whatever the virtual class there is. Some operator, take it straight, and I think it's okay. You're saying so this operator that I mentioned just like has nice commutation relation with the right, but I said the fact that it has nice commutation relation, I think that the only input into that is that I choose my half of the quiver so that the framing spaces only receive maps. That's all I need. And then this nice commutation relation determine the operator. Exactly, yeah. For some special right, again, this will be still, of course, this will be still this quantization business, yeah. And it makes sense because, like I said, the equations that this vertex function satisfies, they have the shape of this dynamical Weil group, which is also.
Sorry, before we did any specializations or anything, right? Mm-hmm. This would just satisfy the standard QPV in this representation. I guess
So it satisfies this sort of this satisfy as a function of the covariant variable satisfies QKZ is a function of the Z variables that satisfies whatever dynamical equation. And the dynamical equation, you can say that's the unique equation that commutes with QKZ. But if you think of the origin of the dynamical equation, that was studied in connection with the traces of intertwining specifically. So this the notion of dynamical equation and dynamical Weil group that was specifically introduced to write down equations that such traces satisfy. So. No, we cannot. I mean, if an operator, if it commutes with EK and FK, that means commutes with everybody. But Verm is irreducible for generic case, so you can't really.
This ratio, like decreasing the ratio between y and epsilon, you don't see
No, but you can move it by. Of course, you can move it by. You can move it by a multiple of. Yeah, right. It means it's an operator from Verma to Verma. I mean, this operator here. It's an operator from Verma to Verma. Yeah, the same. Yeah. I mean, this is the trace in some representation. So if you have one operator, this will generate many other by action of your group, right? So this will generate some space of operators, right? And so then what? Then right. And if you have a so to say you have a space of operators, that's equivalent to saying I have a map from my space to another space tensor some auxiliary space. By picking different linear functions here, I get different operators. And then it says this map now this map actually commutes with my group action because I use the group action to make it act here. Right? And now I say I'm going to pick a specific operator. That means I'm going to pick a specific coordinate here, which is to say I'm going to project on whatever the highest or the lowest vector. Okay, so now I'm sure you. So this I have something. I have to somehow justify being invited to seminar. I have to say something which I consider to be worth discussion, and so so this I consider to be a good problem to study. And now I want some kind of interesting fact to discuss, which I don't understand so super well, but let me. So I sometimes like to talk about automorphic forms, like, pretending I understand something about them. And in automorphic form context, you don't really see Verma modules, but you see more, you'd rather see kind of principal series representation. Principal series representation. G. And in this principal series representation, you can have, this can maybe have a k fixed vector, may have Whittaker linear functional. So this means where k is the maximal compact, and vertical linear functional means it has its eigenvector of the unipotent, this nilpotent subgroup of G. And so this is so that you how for SL2R, what is this? For SL2R, we're asking for functions. We will look at, so principal series as functions. We look at functions on, let's say, functions on R2 minus the origin, such that f of x, y, maybe f of lambda x, lambda y, let's say this is absolute value, lambda to some power, whatever, alpha times f of x, y. And so then, of course, such a function is, of course, uniquely determined. You can restrict it to and then, of course, the group acts on it in the obvious way, and then you restrict it uniquely determined by restriction to S1, but then maybe plus minus, and this is because minus 1 is okay here. This is the same as RP1. And in general, this is which is kind of like, you know, G mod B in this instance. Right? And so this, and so what is the k what is the k fixed vector here? The k fixed vector is something like absolute value square, sorry, x square plus y square to the power alpha over 2. That's the k fixed vector. And the Whittaker functional is integration. It's an integration with some kind of, maybe integrate some kind of Whittaker. So this is this k fixed vector, and Whittaker linear functional is something psi. So this is fk is fixed 1, and this is something like integral of f of, let's say 1 is y is x1 exponential whatever. I mean, Whittaker has some parameter, maybe over 2 pi I m. It doesn't really matter. 2 pi I m x dx. This sort of thing. And so you integrate along the line. This is the orbit. This is the orbit of the. This is an orbit. And to be a non-trivial, if you're going to have an interesting, what are the interesting eigenvalues for n? If I have, right? I mean, if I have, this is n orbit, n is isomorphic to R, and I have an interesting character for R is this. Right? And so this is, and then if you pair kind of the basic statement, if you pair k fixed with Whittaker, then I get a tau eigen. And that's specific. This is going to be specific kind of. You pair k fixed with Whittaker, get a tau eigenfunction, but specific eigenfunction. With specific asymptotic behavior. Maybe you take psi of fk, the specific tau eigenfunction. So now, so here's this all functions here. So of course, all functions on RP1. Well, in this late in the talk, let's just wait. It's a physics seminar too, so it's kind of like holomorphic functions, or rather, sections of a holomorphic. Sections of a holomorphic bundle on CP1. And here we took all functions, but really we really kind of so if we want a function in a chart, then this would be of course this some kind of transition function. We can, in other words, we have one chart where I fix x to be 1 and another chart where I fix y to be 1, and then do some kind of transition between these two. And then when we function in the chart, then we can complexify. If we have any kind of real function, we can think of this being a holomorphic function with complexification, and then there'll be some sort of transition between these things. So, that is very, very close to Verma. So this has some kind of this is some kind of decomposition into Vermas. And this has a specific corollary that if I have this specific towed eigenfunction, I can write as a sum of the corresponding sum over kind of W mini, bar group mini, Verma, kind of some kind of Verma over Verma. In other words, I look at in each Verma, so there'll be W many charts here, and there'll be W many terms, and in each Verma there will be some its own Whittaker functional and the k-fix vector. What? Wild group. In general. So in general, there's the space of though the equation has as many W many solutions, I look at the one which has a particular so for instance in SL2, so this is the ones which are there's the one that's relevant here is the one that has some specific asymptotic at 1 infinity, and this will be decomposed into sum of two solutions that have a specific asymptotic at the other. And so then it's a question. So how to interpret this? So in general, I have this sort of vision or delusion or something or other, where I'd like to do automorphic form computation in this kind of enumerative setup. And you can ask, what are these vectors in terms of the quasi-map realization of Verma modules? So for Whittaker, that was known since Braverman at least. So at least this is how Braverman was proving this Nekrasov conjecture. So this at least at latest Braverman, maybe before him, I don't know. Says that Psi for Quasimaps is just really integration. You have cohomology, some spaces, just integrate, push forward to a point. Or maybe cohomology is like z to the degree, and that z is z is the analog of M. We're interested. We're interested. So this says we're interested in so so if I have a torus, the torus acts on all characters of. If I just rescale by a torus, that conjugates n non-trivial and acts on all the non-trivial characters of n can be permuted with one another, and then all non-degenerate characters will be permuted with one another. And so it doesn't really matter which one I put here, but if it's that this variable here is analogous to the variable m here. And so now I have to tell you what is the k fixed vector, and so then there are two cases. So we complexify here everything, right? So we're doing first of all we're doing GLN, and second in this business we complexify. This is the Quasimaps. They're really insensitive with what sort of coefficients I consider, but you should think of this as a representation of a whatever split form over an algebraic equality, something like that. So that's that sort of stuff in kind of a split representation. So now for Quasimaps, there's so I wanted this complexification story, and of course this will, if I have GL and R, so I have two possibilities. I have GL and R, and then contains O and R. So if I complexify I, maybe SO, they'll say take the connected one. So this is complexify. We're going to get GL and C contains SO and C. Or we can have GL and C, and then this contains UN. And we complexify, what's it going to be? So this is UN, this is a fixed locus. This means what? The fixed locus of what? G has to be equal to G minus star. The inverse star, right? And so now complex. So this is annoying because this also need complex conjugation. So we complexify. So this is going to be what? It's going to be GLNC. First we complexify GLNC. So here we all take all functions, right? We think of this as a real Lie group. So when we complexify complex Lie group, we just get two copies of it. And then such that kind of the complex conjugation, it's like acting on Z and Z bar separately. And Z and Z bar the bar involution is that just permutes these two things. And so here, therefore the fixed locus, I look, again, it's going to be GLN, but it's going to be of the form I take G, and it has to be when I permute the two. So complex conjugation is a permutation, so I'm going to get minus transpose, right? So this is GLN C embedded here. So I have to either give you in one Quasimap, I have to give, so this is my pair. So I have in Quasimaps, I have to give you a fixed vector with respect to orthogonal. And in two Quasimaps, I have to give you a fixed vector with respect to this one. And so then this is, so there's the answer. And the easier the second. So I have Quasimaps cross Quasimaps. I have inclusion, it's just permutation. So just the diagonal. So in other words, the fixed locus of the permutation. That is a fixed. So if I look at the virtual cycle of the diagonally embedded Quasimaps, that is a k-fixed vector. But then this is kind of a little, maybe slightly unexpected. This is the fixed locus of what? Of, so I take sigma, says Quasimaps from P1 to X itself. And what it does, it takes, so there is a coordinate z here, and you send it to minus z. In other words, the Quasimaps, the fixed Quasimaps are the ones that are 2-to-1 cover of another Quasimap. And this has a kind of explanation is that if I want to map this toda of this, the toda over there, this toda, so it's like Givental's toda. So then there will be a doubling of degrees because, so what's the Givental toda? Givental toda is that Givental toda in this context is that you apply the Whittaker function to the Whittaker vector, which is the fundamental cycle. And so then, but here if we want to play to the k-fixed vector, means you have to take the first fundamental cycle, then 2-to-1 cover it, and then apply the Whittaker function. And so that means it was really take all degrees and just double. And similarly here, this map kind of doubles the degrees. How are you? How are you going to count the degrees? This degrees here to get them. Not sure. I mean, just says that my I have a geometric realization of my space, and the k-fixed vector is actual fixed locus of a certain involution. But the involution, it's a little funny. Like instead of this is a little bit like, I don't know. This is a little bit like, whenever we talk about folding, you always say that in the folded situation, this sort of thing has to go hand in hand. So this is like the same price as folding. So here just really take the Dynkin diagram and fold it. So here we took two Dynkin diagram and exchanged them. And okay, this is somehow, but here we took a Dynkin diagram and fold it. And he says then what you're supposed to do on Quasimaps is you take the 2-to-1.
Don't fold X.
No, don't fold X. No.
Because you can also take like the Verma for
No, that's not. No, that's not what it's somehow. That's what it is. And the proof of that is not. I mean, the proof of this part is kind of easy. The proof of that part is not hard. I mean, just if you just look at the formulas that I wrote, give you some formulas, and what's supposed to happen is that's supposed to happen that if I have an even Quasimap and I add a box to that, then there is another even Quasimap of which the same guy is subtractable, and you have to check that the corresponding there's some relation between those things, and that somehow really pans out. Look! I mean, this is. If you ask me, somehow the hardest thing for me is somehow. I mean, I don't know. I mean, you can. Maybe maybe this will teach us something about like all this business is how we're supposed to get the boundary Knizhnik homological equation. Or maybe Min already knows how we're supposed to get there. Exactly, yeah. Exactly. Yeah, but you always told that in this kind of folded situation, this sort of things you have to also introduce.
No, you didn't. Not in the fold. Not in our class fold.
No, not. Okay.
Just after the big diagram.
Just the thing diagram.
Yeah, just the diagram.
Okay. Well, here, this is here. What I thought I learned from you that this is not unusual, but maybe I misunderstood what you were saying. You said there was some kind of when you have this some kind of you want to do some kind of 3D mirror symmetry for this kind of fold. It's totally this thing because that's supposed to be some kind of legless duality going on here, right? I mean, on one hand, I have a principal series representation for G, and then I'm expressing some kind of quantity, some sort of thing. I mean, this is like a, and I'm supposed to say what it is in some kind of legless dual situation. So the fact that the GLN acts on Quasimaps to GLN-like varieties just because the GLN is Langland's self-dual. In general, you have some kind of notion of maps to G, then some kind of G check is supposed to. In particular, this given tal tode is the tode for G check. But so here says that upon this kind of k fixed business, then you get this.
Yeah, no, the other, I'm not sure I remember how it works. It might very well be that they're fine.
Okay, so that's this. I don't know. Say again?
Like if I want to get back the real situation.
But our representations are in like cohomology of something, right? So of course you can take the cohomology of real Quasimaps, but that I think has, I'm not sure what is that. What's that? That doesn't really matter. This is the same kind of representation. I mean, it's just representation wise, it's just really not different. The homology with whatever coefficients is just going to be just Verma module for your Lie algebra with those coefficients. So that's not.
I didn't understand your story about the vertex function.